We'll start the second part. So in the first part, I introduced a bit about distributed inference latent variable models. And just one point I want to recap. I was talking to UIT, and we were discussing this. I think the questions that came about GIP sampling is slow. And actually, there is one point actually I want to address. Is that one way of looking at GIP sampling is that people think that you have to do a couple of iterations to burn in, and then you sample from the posterior. And then when you do an evaluation, you have to take this sample from your posterior and then average them to do your inference. That's one way of using Bayesian inference. But another way, which actually what we use here and what we use in the application, which I will cover next, is that you actually care about only going to one mode of the distribution and take this mode and then use it after that. It's exactly like what you do in optimization. So in optimization, you might have a number of local minima, and you only go to one of these local minima. Same thing in GIP sampling. It doesn't mix because sometimes it doesn't go between modes, but it's needed. As long as it catches one mode, you just use it in your inference. So one view of GIP sampling is just a hill climbing algorithm. It's an optimization algorithm that does hill climbing on the log likelihood until you go a state which is high probability, and then you use it for your inference. So so when you hear about GIP sampling, you should keep in mind: do we care about mixing? Do we care about having multiple modes of the distribution? It's good if you have that, but most of the time, as we do in optimization, we just get one mode and work with it. But Bayesian inference have more advantage than just frequent approach, because you can handle overfitting automatically. You can handle model size by your priors. As you've seen here, if you put a Dirichlet prior, you get some sparsity. And as you have seen in next 2 days, if you get Bayesian number metric, you can control the number of topics and so on. So you can do a lot of cool things that you can do with your optimization technique. OK. So what I will cover next, I have a couple of things that I need to cover, and based on the time and our interaction, we'll cover as many as we can. Most of the flavor of this session is that I will look at applications that we see in industry, and we'll try to formulate them using some latent variable models, sometime using optimization, and then we'll try to see how we can use the ideas from the first part to scale the inference algorithm to the size of the data that you can see at Yahoo or Google. So some of this work was done while I was at Yahoo, so that's why you'll see a data set, but we are doing the same thing at Google as well. So all of these things are very practical, and you probably have been using something in your laptop which is built on top of them. OK. So as we said there's two modes of optimization, one asynchronous and one synchronous. And in your asynchronous optimization, it's log-free, so you don't have to wait for the machines. The machine have different speeds, and you are just synchronizing your parameter in the background. Okay? And this is very good because you don't block. But the bad thing is that if you are not careful with your synchronization, things can go bad, because you can't control how the parameter can diverge very easily across machines. So the advantage is that there's no blocking. The disadvantage is that you have to be really careful when synchronization. So most of the research in a synchronous algorithm is how you come up with efficient synchronization algorithms so that you prevent this diversion from happening. Synchronous algorithms are very nice because you don't have this problem. You can have an algorithm like EM, for example, that run in single machine, and you can just take one step which computes sufficient statistics and just parallelize it. So synchronous algorithm does not change the semantic of the model, but just make it faster. Okay? The problem with synchronous algorithms is that you require a barrier step. So you do something, you wait for everyone to finish. And the problem with that is that you are as fast as the slowest machine. So most of the research in synchronous algorithm is about how you can make, how you break the dependence in the slowest machine. Like you can reschedule the slow machine. You can do some you run multiple copies and take the ones that finishes fast. So there's a lot of work here. Okay. Sometime we can start with synchronous algorithms like what we see today in the second part, and we turn it into a synchronous algorithm. And I'll show you the huge difference in performance. Sometimes we can't. Okay? So sometimes it's an open problem. So you need to be familiar with the two optimization techniques, two synchronization techniques. OK, so we'll take one. Some of the application I will cover today is how we model user interest. Like if you are at Google or Yahoo or user come, and user interact with Google. For example, he watched different YouTube videos. He pushes some queries into Google. So we have a list of activities about each user, and I want, in an unsupervised way, to extract some topics or some interests, and then represent each user as a distribution over this interest, and we see how these distributions change over time. Okay? And I want to do this inference in a language-independent way and unsupervised. For example, this user here, he was interested in baseball, and then suddenly he started interested in finance, then starts looking in job, his interest in baseball goes down, and so on. So this is very useful, and I will show you why you can use this to actually applications that make money for web companies. Second application, multi-domain personalization. Usually when you interact with the web, for example, we have what movies you like, what news article you like. So you have different domain, you interact with different properties. For example, if you come to Google, you can interact with YouTube, you watch some videos, you can interact with search queries, you can interact with the news. And the question which we want to address here, can we actually combine your interaction with different properties so that we can learn something about the user? Like, if you haven't watched it, if you haven't went to YouTube, but I know what news you read, can I actually recommend some videos for you to watch, even though you haven't went to YouTube before? So that's what we call multi-domain personalization. Third application we'll talk about is graph factorization or social network analysis. And in this case, you have, in addition to have the user-item interactions, you already have information between user-user interaction. For example, I know which users have talked to each other using the messenger, or you have the G+ connection between the users, how frequent you communicate with each other on social networks. And the question is, can we actually combine these two things so that I have better recommendation if I know more about your neighbors than I know about you? Combine these two graphs. Couple of other applications is in computational advertising, and the idea here is that we model user interests, but here I want to model like advertisers. So here's one form of display advertising where when you go to a news website like Yahoo or Google, you find these ads on the right-hand side, which for you might look annoying, but the idea is that by user modeling, we want to show you something which is actually useful, something you're actually looking for. And in this thing, we want to optimize things for the advertiser. So if the advertiser want to show an ad, we want to compute two things. What is the probability that the user click on the ad? And the other thing is that if the user click on the ad and went to the advertiser website, we want to predict will the user buy the product or not. And this is called conversion optimization. And sometimes we want to actually have data. You have lots of data about clicks, but you have few positive examples about conversion. And the question here, can we actually combine these two sources of information so that we have reliable prediction about if I show you an ad, whether you go and buy the product or not? And if we have that, then we can maximize which ad to show you, because you need to maximize revenue for the advertiser. Okay, so we'll start with the first one about multi-domain personalization. And as I say, the problem is that you have, let's say in Google, you have multiple properties and you interact with different properties. I want to combine all of these interactions so I can have a unified profile construction about the user. I want to say this user interested in these topics, and these topics manifest itself in YouTube, in these keywords, or in these videos, and this topic manifests itself in news in this article. For example, people who like to read about celebrity in the news will like about entertainment videos in YouTube, and so on. People who like to read about scientific articles in the news may be interested in about Discovery Channel in YouTube, and so on. So we would like to learn these things so that given one interaction, I can predict interaction of different property. And what I mean by interaction is just a bag of words describing the objects that the user interact with in a given domain. For example, that if you interact with the news, that would be a keyword in the articles that you clicked in. If you interact with a YouTube video, then the interaction will be the tags assigned to that YouTube video, and so on. So that's one way of representing that interaction. Okay, so the way it works is that you have some user meta profile, which tell you what the user is interested in, and then we have some way of projecting that meta profile into to get the user music profile, user news profile, and then you put personalized news, and then if the user now doesn't see any movie before, I can use this meta profile to give you also a movie profile, so I can recommend some movies even though you haven't watched movies before. Okay? And in recommendation, if you're familiar with this, we call this cold start problem. Like if you go to the YouTube, for example, and you haven't watched any video, I still want to recommend something for you based on your interaction with news and, for example, Google Play Store. Okay, and here's one way we can model this problem. Again, we use build on top of LDAs that we discussed in the first part. So for a given user, so the outer block is the user, and the user interact with different domains. And we model the interaction with every domain as an LDA. So the user have a distribution over topics in that domain. And for each interaction, you just model an LDA, you sample a topic from this theta, and then you sample the interaction from that distribution over keywords. So in this case, the user have different theta for each domains, and for each topic, it has different distribution over the vocabulary of each domain. Okay? So now we need to have what's the prior distribution. And this is where all, currently they are independent, there's nothing new, it's just independent LDA, but we need to couple this. And the ways that we couple this is that we say that the user have some meta profile features, okay? And the prior distribution over the user theta over a given domain, you can get it by multiplying this meta feature, which is a vector of length k, over a projection matrix for a given domain. So each domain has a projection matrix which map from k-dimensional space into the topic, from the feature space to the topic distribution. Okay? So all what this means is that the user topics over that domain is function over the user feature and the domain transformation matrix. Okay? So the generative process is that we say, okay, the prior distribution over the topic for a given domain is a logit function, and the logit function this is a vector time matrix, it exponentiated, add 1 takes the log, so you end up with a vector over alpha. Okay? And if you have the same meta vector and different projection matrix, you have different prior distribution for every domain for a given user. Okay? So now, instead of having each domain as a separate LDA, now you couple them by coupling the prior via the user features. Okay? And the user features, you can think about it. It can be demographic, it can be the age, male, female, and so on. But in this application, we'll go to the extreme, and we also model the feature as latent variables. Okay? So I don't know what the user features are. And I want to learn the user feature and the projection matrix so that I try to learn some association between the domains. Okay, again, using our, explaining the same idea again. So we have, for the user meta profile, you have some feature, and then each domain has a projection matrix, and then you use the logit function to get the user interest over this domain as a function of the user meta feature and the domain projection matrix. Okay? Okay, and this is just different way of saying the same thing. You have 3 users, each one has 3 features, and you have 3 domains, and each domain has different transformation matrix. And you just want to discover what's the user taste in news. You get alpha as a logit transformation between these 2 products. And then you have an LDA model. You generate the interaction. If you have another user, you can, again, use the same thing. You combine the user feature with the domain projection matrix, and then you have another LDA and so on. Okay? And once you have all of these metrics, you want to learn them jointly. And the goal of inference is to discover the user feature and the transformation matrix. So what's the advantage now? If this user, for example, user 3, haven't interacted with movies before, so now based on his interaction with music, I can learn X3. And based on other user interaction of movies, I can learn lambda 3. And now I combine X3 with lambda 3 to get the user interaction with music. So I can generalize to things that I haven't seen before. Okay. So how we can do inference here? So we have 2 parts. The first part is that we need to joint optimization over, so we collapse, as before, we collapse everything, we collapse theta, we collapse phi, and you get a joint distribution over z, x, and lambda. And you want to optimize, get the posterior over this. So what we do is that fixing lambda and x, you can just get alpha and just throw them away. And given alpha and collapsing theta and phi, this is just an LDA. So you can use the collapsed asynchronous algorithm that I described in the first iteration. Okay? And now you have Z, so fixing the Z's, you need to optimize X and optimize lambda, and you can do that using standard techniques like LBGFS or gradient descent. Okay? The problem here is that, again, we can divide this into local and global when you talk about optimization between lambda and X. So the local now would be X, because this is specific to each user, and the global will be lambda for each domain, because this is shared across the users. And fixing the Z, you still want to optimize lambda, and there is actually no asynchronous algorithm now. So we have to do synchronous optimization step. And the way it goes is that you sample Z's for all users, fixing the features, X and lambda. And once you do a few iterations, you now need to optimize lambda, condition on Z and X. And in order to do that, say, if you think about it, how you can do that in single machine, you just do one pass over the data, compute some statistic, which is the gradient, and then apply a step over lambda. So you do the same thing here, but in distributed format. So you go over your data, you compute the gradient, you reach a barrier, you have one machine go and collect this gradient and do optimization step over the parameter and write it back, and then all the machine will read it and continue again. Okay? So that's very simple. So again, you have here a synchronous algorithm, and then we have here a synchronous step, and then you iterate these two things again. Okay? So how it works? So we did this work at Yahoo, and we have two domains. We have the user interaction with the front page, and we have the user interaction with the news article. And at that time, we have like a few million users, and we measure the gain relative to independent model. So we can build an LDA model over front page, an LDA model over news, and we can do different recommendations independently. But using this model, we can combine from front page and the news and see if we can leverage, if a user heavily usage of front page, does this actually improve our recommendation over news and not, and so forth. So as we say, like we don't only have different number of topics, but we only have a number of latent features. So here is the gain over as a front page and in news, the gain in recommendation accuracy. And as you can see, as you increase with 25 or 50, you see that the gain, you always gain over an independent model, but the gain decrease when you increase the number of features because you overfit. So you have still model selection problem, how many features you use here. And here is some of the topic, because if you remember here, I remember the model, you have a distribution, topic distribution over each domain. So the topic has two language models, one over news and one over front page. And what we have learned here is that people who look at celebrity in the front page read news about entertainment. And people who look at science in the front page read news about science fiction. And it's something that you expect to see. Okay? So again, the idea here is that if I have a user now who have interacted in the front page and I know that he have interest in science, even though I haven't seen him reading news article, I can now know what to recommend to him based on the science distribution over news article. Okay, so that solves the cold starter problem. Okay. Okay, so that's one application. Second application is how we can track user interest. So one way to characterize user interest is it's short-term versus long-term. So what does this mean? Means for this user over time, this user have a long-term interest in music, but here he have a short-term interest in housing. He was moving, for example. After some time, he starts looking for furniture. You want to buy a car. Sometime he has travel plans. So if I actually know this information about the user, it's very important because now I can know what content to show to the user at different time. But we don't observe that. This is latent. What we actually observe is that we observe when the user comes to the website, whether it's Yahoo or Google or Facebook, we observe what content, like what pages the user views, what queries the user issues. And given this information over time, we want to go back and learn a trend distribution over each interest. So you want to first classify this into interest and track this interest over time. Okay. So the formulation of the problem is that the input is that you have the queries issued by the user, or for example, the tag of watched videos, and you have some of the news articles that the user read, and you have a timestamp of all of these sections. And the output is that we want to have a user daily distribution over interest. All of this should be dynamic, so we should be able to discover what are the interest representation, and the interest should be dynamic, both in terms of the interest distribution over keywords and the interest trend over time. And we'd like this inference to be online and scalable. So each day you get user interaction, need to update the user model in a daily basis. And we'd like this also to be language independent so that we don't involve editors in the process. So it should be unsupervised technique. For example, here's some cartoonish view. Here is the user. Here's some of the queries or some of the tags that he interacted with. And given this, we want to see that the user have an interest in travel. This actually has increasing, and then it decays slowly. Then he starts back to school. He starts looking for loans and so on, and then he starts interest in finance and so on. Okay. So why is this important? Because if I want to show user a financing ad, I have to show it here when the user interest in finance is going up. So modeling this trend is very important when we want to target the user with content. If you show, even though it's a user, if you want to show a financing ad, you should show it here, not here, because here the user have no interest in finance. And if you show it here, the user probably will click on it and you make money. Same thing if a user want to show an ad hotel, you don't want to show it here, you just want to show it when the user actually interest in travel was going up, not was going down. That's very important. Okay? So getting this dynamic information has the advantage that you can target the user with relevant material at the right time. Sure.
Does it matter that sometimes my interest doesn't die gradually, it dies suddenly? So
yes. So the main assumption in the models that I'm talking is that that assumes some decay if I don't observe anything about the user. And we model decay as smooth, but with different exponent. So you can get the same sudden smooth by having like a very smooth but sharp decay. Sure? Okay. So yeah, we model that. So we model the slope. As you can see here, your interest in travel is decayed slowly, but your interest in finance is decayed more sharply. Okay. So we'll discover that as well. And that actually is a property of the topic itself, or the interest. Okay. So how? Sure. Yeah.
So do you model the interest of a user based on the interest of other users? Like,
yes. Yes.
So suppose I have followed a user for 10 years. I have followed a user for 10 years, for example. So I know the pattern, and I have a young user now. I can see that this user also has a tendency to follow the same pattern as the old one. So I can predict like okay.
Sure. So we don't do that in this model, but I will show you how you do that. Okay. So what we are talking about is that user who start looking back to school, after some time start looking for finance. Right? So that would be a Markov model, where you see if the user interest in back to school topic peaks, then you expect that the user interest in the topic finance will peak after some time. So you model it this way. I will show just independent, but you can add, I will show you how you can extend the model to have a dynamic first order Markov property. That's a good question, actually. More questions? Okay. So how we can formulate this? There are many ways to formulate this problem, but one way to formulate it as you probably have expected, as a mixed membership model, as a topic model, is that you can model each user as an object or as a bag of words. And the words is just the user interactions, which is just the keywords that you observe, the queries, the tags of the videos the user watches, and so on. Okay? And now you can model each interest or each mixture as a distribution over the words themselves, the interaction words themselves. So for example, you might have a topic that models the user interest in diet, and for this topic, you will find words like recipe, pizza, food, chocolate, so on in the user interaction with content. If the user is looking for car, you will find these words in the user queries, and so on. Okay? And now I can model each user as a distribution over the topic. So this user, for example, is interested in looking for a job and looking for a car. And this user have a large interest in diet, but he's also interested in finance. Okay? And this is one way to model this problem. So I look at the queries and try to come up with latent topic and distribution of the user over the topic. But this model is static, and you want to make it dynamic. Yeah? Okay. So in graphical notation, this is the LDA model as before. The only difference here is that before we have the probability of theta condition on the prior. Here I had a factor distribution of the prior. So if you remember before, when you model the distribution distribution, there are two ways of modeling the distribution distribution. One way is to say, so remember we say if theta is treated as especially alpha 1 until alpha k. So the mean, the expected value of theta I, alpha I over summation, right? But this is scale invariant. So you can scale all of this alpha and still have the same mean, okay? But the magnitude of alpha will give you like how much the sample value of theta deviate around this mean, okay? So another way of just modeling this is to say, instead of having a single parameter, you say you have two parameters. You say theta is a Dirichlet distribution with lambda time omega. So omega is a distribution, right? And this will give you the mean of theta. And lambda is a scaling factor, will give you how the variance of theta around that mean. So if lambda is large, you have small variance around the mean. If lambda is small, you have a large variance around the mean. Okay? This is equivalent to this. Okay? So in this case, omega will equal this thing, and lambda will just be the scaling. Okay? So the way we model this here is that we say, okay, the prior distribution is theta condition on lambda, which is a scaling factor, scaling parameter, and omega, which is the mean of theta. And is the Dirichlet distribution now parameterized by the product of these. So omega is a vector and lambda is a scalar. It's just the same thing, just different parameterization. Okay? And now I can go one layer up and say that omega itself is a distribution from another Dirichlet distribution with alpha. Okay? Because omega is a distribution, is a vector that sum up to 1, so I can put a prior over it as a Dirichlet distribution. So the generative model will go like that. I first sample a mean from a Dirichlet distribution with alpha over k. So it's a symmetric Dirichlet distribution, and the precision is alpha over k, not k is number of topic. And then I draw a topic for each word, for each distribution for each topic as a multinomial over a given vocabulary from a Dirichlet parameterized by beta. And then I have an LDA model after that where I draw theta from lambda time omega, and the LDA model goes after that. And I will show you why this is important for tracking. And just giving a hint why it's important, because if I want to evolve the mean distribution of the topic, I want to evolve this omega. Okay? And now this omega is constrained over assembly, so it's easy to evolve it over time. Right? It's hard if I have this like as one parameter. Okay? This is different parameterization for LDA. Okay, so I think in 2 days we'll talk more about Bayesian non-parametric, but today I just want to give you another intuition about LDA generative process, and then using to motivate the dynamic extension. So one way of explaining LDA here is that you can collapse theta and omega, okay? And that will give you something called the Polya-Urn representation. Okay? And the Polya-Urn representation is just giving you a distribution, like each document have higher probability of reusing the topic that appeared before in this document. So in graphic notation, you have a global distribution over topic. You have like 4 topics. You have a global distribution over the topics, okay? And you have a local distribution over the topics. This is the user distribution over the topics, okay? And you have a couple of users. These I'm just describing the generative process. And this is called again the Polya-Urn distribution. So in order to generate another interaction for a given user, this is our topic distributions. This is a local distribution of the user over topics. and this is the user interaction. So the generative process proceeds as following. I want to choose a topic from a local distribution, and then I sample a word from that topic distribution. Okay? So with some small probability, instead of sampling from the local distribution, I can, and this small probability is given by lambda. So again, you have a distribution local intent based on the things that appear here, the diet topics. But also I can have with some small probability proportional to lambda, I can introduce a new intent into the user. User can generate a new topic. So if you select to generate a new intent, you now go to the global distribution and you sample one of them based on how much they are used across the users. Okay? So this plays a role of omega, this plays a role of theta, and lambda plays a role of the variance. So if lambda is large, you always sample from the global. And that's why the local distribution will resemble the global across all users. If lambda is small, most of the time you sample from the local distribution, and that's why once you have two topics, you stop going in the global distribution, and each local distribution would have high variance from the global one. This is another way of explaining why you have this sparseness when you have lambda a smaller value. Okay? So again, so generative process, I want to generate a new token, I pick a topic, either I pick a local one or with some small probability I have a new one. And if I pick the existing one, so he user interested in diet, he continue looking for diet when he issue a new query. And when I know that the topic of the new word will be diet, I just go and sample a word from this diet distribution over the vocabulary, get pizza, for example. But for a new word, I, for example, might choose to introduce a new interest for the user. And in this way, I sample the interest from the global distribution. For this case, the user, for example, was looking for car. And now I introduce this interest into the user and then sample this word from the car distribution over the vocabulary, and so on. I continue like that. Okay? This is another way of modeling the LDA generative process. This is called the Polya-Urn Representation. And the reason here is that you have tendency to reuse what you have been doing before than just introducing a new topic. Okay? Is clear? And again, we can relate these things now if you go back. You can look here. So lambda, as I said before, models the variance, and omega models the mean. And if lambda is high, most of the time you go and sample z from omega. Okay? And that's why theta in marginalization will look like omega most of the time. But if lambda is small, so once you sample a few keywords, you just stick sampling from what have appeared before. Okay? And that's another way of explaining the sparsity behavior of the dictionary distribution. If you allow the global topic to evolve, like you have a number of metric ways, then this is called the Chinese franchise process, and hopefully in 2 days you'll hear more about that. Okay? This is just a fixed dimensional version of it. Okay. So now we generate, and now we reverse the process and do sampling. So I'm not going to talk about that. The sampling will be exactly like before. But the problem here is that this static model, it doesn't evolve the user interest over time. The user interest in diet and cars, and I don't know how this change over time. It doesn't involve the trends. For example, if a new car appears in the market, the global interest in the cars will skyrocket. So I have to, if I want to show an ad, I probably will show an ad about cars, even though the user haven't seen car before, because everyone else is looking for cars, so probably car is a popular topic. And also the topic distribution over words does not evolve over time. And we need to fix that. We need to evolve all of these things. Okay, so to make a dynamic model, we say, okay, this is the state of the model at time t. I want to have a projection step to see how things will look at time t plus 1. So in generative process, I finish generating the user interaction at time t, and now I want to generate the user interaction at time t plus 1. Okay, so there are 3 components of the model: how the global popularity of the topic will look like, and how the local popularity will look like. So one intuition is that at time t plus 1 is a topic where popular at time t will still continue to be popular at time t plus 1, but probably I will decay them a little bit using some exponential decay factor. And if someone asks here about topic appear sharply, decay sharply, so if lambda is actually large, then the topic decay quicker. If lambda small, then the topic popular here still become popular again. Okay, so you can model on a bare topic basis how fast the topic interest decay over time. Okay, so we can do that. We can start with this as a prior in time t plus 1, and this prior is just we look at the usage at time t and we multiply it by some exponential decay factor. Okay, so we fixed this problem. The second part is that the topic distribution over the vocabulary, we do the same thing. We expect that the topic distribution at time t plus 1, it will be still a ratio distribution, but I take the mean to be the previous topic at time t. It's just a random walk from the current state of the topic. Okay, that's very simple. And the intuition here is that most of the time the word will remain the same, but some new word might appear, and some word might change. Interest, for example, a new release of the car come in, so people who are interested in car start to search for this word, so I need to update the topic distribution to reflect that. Okay, and that's the intuition. So just allow for random noise to be added to the topic distribution. So the hardest part is the user distribution over topic. How I can say something about what the user would be looking at t plus 1, given what the user had been doing from time 1 to time t. Okay. The problem here is that can we really use exponential decay as we use for the global trend? Probably it's not a good idea, right? Because if I use exponential decay, probably I won't discover global and short-term and long-term trend. And user interests actually are more like periodic, and it decays with different frequency. So we would like to have some dynamic model that allows us to capture the short-term and the long-term interest of the user at time t plus 1. So one way of doing that, so I look at what the user has been doing from time 1 to time t, and I already have a topic assignment for each interaction. Okay, and I want to say something about what the user will be looking for at time t plus 1. And one way of looking at that, you can look at this distribution at multiple scales. So for example, if you look at static model, you see that the user mostly, if you look at all interaction, is interested in diet, with some probability interested in cars, and somehow about jobs. You can look at this as a long-term interest. If you do the same thing, but looking at the last month, you see that in the last month, he's actually more interested in looking for a job than the other two things. And if you look at the last week, he's actually more interested in looking for cars than anything else. Okay? So now I have short-term interest, long-term interest, and medium-term interest. And in order to get a prior at time t plus 1, I just need to combine these three things. So even though the user in the short term, he was only looking for cars, he still might look for jobs because these things might decay slowly than before. Okay? So I need to combine these three by just giving weight to each distribution. And you need to scale this mu. So mu is number between 0 and 1. And that's why when you mu square is smaller than mu cube is smaller than m. And this actually will give you like how volatile the user interests are. So if mu is very small, then most of the user action at time t plus 1 will be driven by the short-term interest, because these ones will, when you exponentiate them, will go to 0 almost. If mu is closer to 1, then user is really static. His interest doesn't change that much, because most of the time, the interest at time t plus 1 will be driven by the global interest, because mu is close to 1, and this one is aggregate over a large distribution. Okay? So this like multi-scale prior allows us to capture this short versus long-term interest. And you can learn mu for each user separately. So you can know which user volatility pattern looks like. Okay? So back to our model. We compute prior at time t plus 1 by combining what the user have been doing from time 1 to time t. And now once you have the global prior, the user prior, I just treat this as pseudo counts, and I start the generative process from here. So again, for here, if I want to sample an interaction from the user, I look at the local distribution. These are pseudo counts, so I can use them. I can either take one of them and continue generating an interaction from one of them, or I can have a new one. And when I sample a new interaction, I just look at the global distribution and do the same thing. So I just have a head start at time t plus 1 in the generative process. Okay? Okay. So I started with an LDA, and then I collapsed some variables, theta and omega, and show you like equivalent Polya-Urn representation. And then it was easier to extend it over time, and this is how the global process evolve over time, and this is how the user process evolve. And as you can see that the global process is dense because the topic appears at each time step, but the user interaction is sparse because I might not see the user at time t plus 2. So a time here might be a day, for example. So I might see the user interaction in Saturday, I don't see the user on Sunday, and might see the user on Saturday, beginning of the week and end of the week, and that's why you need to have this multi-scale, otherwise you will forget about what the user have been doing before. So we have this model based in generalizing the Polya-Urn representation, but how this looks like in graphical notation. And just to quicker, it's not hard. So again, as we take the Polya-Urn and say, okay, this is a slice at time t, and then we evolve it over time, we say same. We seem that take the LD model, but we just prefix everything with time t. And you have omega t, you have the user distribution, user I distribution at time t, and so on, and you have the topic distribution at time t. And instead of sampling omega from the prior alpha, you sample omega from a posterior, which is alpha, but you shift alpha by how frequent that this topic was in the previous time step. So you have a shifted prior, okay? And same thing for, and this mu m is just the popularity, the decayed popularity, as I said before. Just take this and apply some exponential kernel, and you get m tilde, okay? And in case of beta, it's the same thing. You can decay these things using an exponential kernel and using them as prior, and you shift your beta with this decayed count of the previous, the topic distribution at time t minus 1. Okay? So again, all what's affected is that the prior over omega, instead of coming from alpha, it just comes from alpha plus some historical Zodo count. Same thing for beta. Instead of coming from beta directly, the prior distribution over the topic comes from beta, shifted but some historic usage count. And then after that, same thing for the user. Instead of sampling the user from omega only, I sample the user interest from omega, right? Shifted by some historic distribution using the multi-scale kernel from what the user had been doing before. Okay? And the generative process after that is just as before. That's very easy. Okay? Just the equivalent between the two representations. Okay, and this is how the process looks like. And as I said, this restaurant, you hear more about this in 2 days. Like, if you want to go number-metric, if I don't know how many topics there are, we generalize this using something called the recurrent Chinese restaurant process, and not going over that today. Okay, so this is a generative model, and currently want to do inference. And as I said, we have hundreds of millions of users, and want to do inference distributed and online. So at each day, we observe something and want to update the user model. So how the workflow looks like? So I have hundreds of millions of users, and given at the end of each day, I have the user interaction. And this granularity of the time can be hour, can be day, can be anything. We use it to be day here. So at the end of each day, we have the user interaction with what queries the user issued, what tags of which the user watched, and so on. And then I have the current user model. I have the current state of the system, like what is the global popularity of each topic, what is the topic distribution. And I want to combine the current state of the system, the current user model, with the observation model at time t, and the prior at time t, and then I combine them to have the user model at time t plus 1. Okay? So that's what we mean by inference, which is the daily update. Create the current model, take the prior, take the observation, and have a new user model, which will be the prior for the next time step. Okay? So how can we do that? So we use a gradient particle filtering algorithm. It's just a gradient algorithm. It actually works very well in practice, and this is another thing that people say, if you use particle filter, you need to have many particles, but this is a case where we don't care about the distribution, we care about the mode. So just one particle that captures the mode is good enough. So the inference problem is that we collapse all multinomial. So mu, m, n, and b, these are constant, and you get this from the previous interaction, which you already have. The latent variable here is just the omega, theta, z, and alpha. So we collapse theta and we collapse alpha. and we only have a posterior distribution over the global popularity and the topic indicator, conditioned on the prior information that you compute using the exponential decay or using the multi-scale decay. Okay, so how we can do distributed inference? As you expected, if we fix omega, now we need to sample z, and you know how to do that from LD, from the beginning of the lecture, right? If omega is fixed, then I just run star synchronization or the asynchronous algorithm that I show you about. Now, fixing z, I want to sample omega, and using that, we need some synchronous operation. Okay? So the same patterns that I described in the previous inference will appear here again. So again, we'll do the same thing. So currently we have it's exactly an LDA model at time t, but it has some prior. So I distribute the data across machines, and now this machine is still coupled because I still have the omega ties m and phi, and then I collapse everything other than omega. So if I collapse theta and I collapse alpha, remember we get the Polya-Urn representation, which looks like that. So for each client, it has a bunch of users, and for each user, it remembers the local distribution of the user and the topic indicator for each word the user interacts with at time t. Okay, and I also have the global distribution, and then we use the trick that we have done before. We just have a global shared memory, which is a parameter server, where we replicate the topic word sufficient statistics. Okay, that will be our global state. This will be the local copies. And now omega will be fixed and just send a copy of omega to h1. And then we do our synchronous operation where I sample a topic for each word. And this is exactly the same probability as you have seen in LDA, except that you have to incorporate the prior. So this is a local count. In LDA, we only have the global prior, but here you have the prior from time t minus 1. Okay? This is the pseudo count at time t. That's the only difference. For the user, how likely the topic appear in the user, you still have the local count at time t plus the prior. The prior now will not be alpha, will be omega, lambda omega. And I saw before the product is equivalent to alpha. But you also have historic information from how the user had been doing in the previous time steps. Okay? But all these tilde things are fixed, so it doesn't affect our inference algorithm. Okay? So actually, it's the same pattern as we have seen before. We use the same algorithm. So you keep sampling locally, and we update the global and local statistics, synchronizing using the asynchronous algorithm. You do that for a few iterations. At the end of each iteration, we want to sample omega, and sampling omega requires something called Antoniak distribution. Again, you probably will hear about these things in the Bayesian number metric session. But all what you need to know is that it requires synchronous operation, and same thing as the pattern before. You do the star sync to assign a word for each topic, and now you want to sample omega. Same thing, compute some sufficient statistic for that, write them to the global state, have one machine go and collect them, sample a new value for omega, and then write it back, and then you continue the iteration again. Okay, so the same template that we have used in the previous application, we'll use it here again, and the same building block, which I discovered in the first part, we'll use it in this stage. Okay, so again, this is a way of like stacking these like building blocks to have more complicated models. Okay, so how it works? This is really fun. Scales, we apply it to two data sets. I just go one of them, the bigger one, where we have, so here is the application. We want to discover the user interest over time. So in one application, we have 13 million users. In another data set, we have like around 30 million users. And for each user, we have a history over 44 days, and as time here would be a day. So we break user interest into day, discrete time steps. And the size of the data here is like half terabyte, here like quarter terabyte. So this is huge, actually. And as I said, like the application here is that once I discover the user interest, I want to use them as feature for a classifier. And this classifier will predict whether the user will click on an ad or not. And for each ad, we call it campaign. Like a user a given advertiser want to have a campaign, for example. I want to have a discount in a trip to Iceland. This is a campaign. I want to predict based on the user interest whether the user will click in this ad if I show it and buy the ticket or not. This is called conversion optimization. Okay? So once I build a model unsupervised, I take this feature and learn a classifier based on other users have clicked or not. The only difference here is that The baseline, or what people use, is that they take the raw feature. They take the queries, they take the website, and they build the classifier on top of that. Here, we take the user raw feature, we build an interest, and then use this interest as our feature to our classifier. Okay, so it's a two-step process. So first thing, like, does this actually result in interpretable models? This is actually what we get when we apply these things over the Yahoo dataset, is that we discover these are queries or keywords from the news articles that the user have read. We discover some topic about dating, baseball, celebrity, and so on. And then, for example, for this user, he was interested in dating, and then suddenly his interest in baseball goes up and dating goes down. And I'm not sure how we can interpret that. He interested in baseball, get dumped down, or he broke up and then have something else. I don't know. And this another user, he was interested in finance, and then suddenly he started looking for a job, and his interest in finance goes down. So something was going as well. So as I said, if I want to target the user with a job ads, it should be at this stage when his interest in job is going up. So these actually give us rich features where you can build a classifier. So when you build a classifier, you build a classifier at each day and use it to predict for the second day. So that's why you get a better tracking of user interest. And the advantage here, if you build a classifier on the keywords versus build a classifier over the interest, is that you get better generalization, because many people will be looking in dating. Some people will use keywords like singles, personals. Others will use dating. So regardless of the service words that you use, both of them will have the same feature to the classifier. But if you work on the raw data, you have to have many data in order to have the same generalization. So these actually will be very useful when you have few labeled examples. And in conversion optimization, the number of positive examples, the number of users who click on the ad and buy the product is very few. And that's why you need to limit the number of features. And that's why topic model helps here a lot. Okay, so how it works is end to end. So one way of measuring classifier performance is the ROC measure, higher is better. And we train 3 classifiers, one classifier based on the raw data, another classifier based on our temporal model, and a third classifier which combined the baseline feature and the topic model feature. So the feature to the classifier is the raw data and the interest as well. Okay. And here is a breakdown of the performance by based on the campaign. So we bend the campaigns based on how many positive examples I have in each campaign. As I told you before, if I want to train a conversion optimization for a given campaign, I look at history information. I have like million of impression meaning that I show the ad to the user. This is called impression. This is a training example. And the response, whether the user click on the ad or not, that will be your label, 0 or 1. So, so based on the number of labels in the campaign, we see that for campaigns that have few labels, topic model actually improve more. For campaigns that have a large number of labels, the improvement becomes less than here, but still huge. So even across the whole spectrum, still using topic model generalizes better over using the raw features, okay, which is really good. And if I just want to combine these things into just take the average of this weighting by the number of conversions to give a single measure. It's bad. Sorry, I myself get. Okay, so we use a weighted ROC measure, which is like summarizing this curve using one number. And here is the baseline, 54 ROC measure. Here is our model if you combine these two. And here is if you use a static model. And if you can see the improvement over the baseline, this is almost 2% improvement, 2-point improvement. In computational advertising, this is huge. 2 point is really huge. This is a lot of money. Okay? So you can still make money in industry with these things. So it's not just fancy models that we like to write and do inference for. These things are very useful in practice. Okay? And in terms of scale, as I told you before, we applied this model. So if you want to see how our algorithm scale, we look at the time per iteration in minutes, and we increase the number of users, but at the same time increase the number of machines. So the way that you read this, here we have 200 million users, and we have 100 machines. If I triple that number of users, then here I have 600 million users, but I have 300 machines. Okay? So the perfect scalability curve should be linear, right? Should be constant, because I double the data and I double the number of machines, or I triple it and triple the number of machines. So the time per iteration should increase, right? If you have perfect scalability. If you fix the number of machines, it goes linearly. But in using our inference algorithm, you see actually we are slightly in the first range when we have 300 machines. It's almost perfect scalability. But if you increase the number of machines, you go to like 1,000 machines. There is a bit of overhead because of communication. Because as I said, we have synchronous operation. So as you increase the number of machines, you'll get some slow machines. So you have to wait a little bit. So it's a little of overhead that you need to incur. And so the iteration time, even though you have multiplied the number of resources by 10 and the data by 10, you still don't get the same time per iteration because there is some communication overhead. Okay? But still, all what I have said here, we apply these things to 2 billion users with 1,000 machines, which is actually a huge scale. And the vocabulary here was around like a few million words. Okay? Any questions? Okay. Skip over this. So okay. So as I said, we talk about asynchronous first using collapsed GIF sampling at the beginning, and then we say like sometimes we still want to do synchronous operation, and we need to mix and match for some variables that you collapse. Maybe actually it's not bad to go over this. So again, so some of the time we collapse some of the variable, other of the time we don't collapse. So if you remember, like in temporal application, we have omega, and we didn't collapse omega. Okay. So if you don't collapse omega, condition on the variable, the children are conditionally independent. So what you do is that it doesn't require a synchronous operation, but it requires some synchronous sampling because you fix the variable, condition on this fixed variable, these children, which is a document topic distribution, become conditionally independent, so you can just run in parallel without any synchronization. And once you have one pass over the data, you use some synchronous operation where you compute statistics, sum them across machine, and then update the global variable, update samples, the uncollapsed variable, and then you push it back and so on. Okay? So if you don't collapse a variable in the graphical model, it's good because it actually makes things independent, which is good for parallelization, but it's actually bad because it makes it slow and it requires some synchronous sampling. If you collapse the variable, for example, when you collapse the topic word distribution, we link all the topic indicator for all the words, so you get something like that. The advantage here is that makes it faster because once you change one random variable, when you sample the new random variable, just use the current value. Okay? Here you have to wait for one pass over the data to propagate the value. You have to wait one pass to propagate it up and propagate it down. But here, like once you change, you sample one variable, condition on the remaining. Now you change that. When you go to sample a new one, you use a most recent value for this variable. So it makes it better, but it hinders parallelism because I said this has to be sequential. But we know how to break that. Okay? So if the variable depend on each other using aggregates, we can use asynchronous communication as I described to synchronize this operation. So whether or not you want to collapse a variable or not, it depends on actually in the importance of these variables. So for example, in our model where we have the topic word distribution, we have to collapse because this is actually very important in the likelihood. If for the case of omega, we didn't collapse because actually it actually the variable does not change fast with the sampling, so it's okay to keep it fixed for the duration of the iteration so that you can save bandwidth and then you can just change it at the end. Okay? So whether or not it collapses or not, this is some art. You need to be familiar with, does this variable change quicker or not? If it changes quick, then you have to collapse. If it doesn't, then you don't collapse. Okay? And all of the decisions have pros and cons. So you have to weigh these things. And this is the art of designing this inference algorithm. So we have a building block when you don't collapse. We have a building block when you collapse. Which one you use, you have to have some experience in that. Okay? There are some guidelines, but at the end of the day, it's an art. Okay. So as I said, I want to switch gear a little bit and talk about other applications where we take some synchronous algorithms and actually convert into asynchronous for optimization. So we can break the barriers that we have said before. So, yes?
So the model that you have shown for the user profile, so don't you think that this model doesn't really show the interest of a user, but it motivates a user to develop interest in a particular direction?
Yeah. So this is called smooth model. Smooth model means look what the user have been doing and try to see how these things decay over time, okay? But it's not a predictive model like the questions that you have asked, because if I want to make it, I remember your question. If I want to make this thing predictive, I would like to learn, we need to add some Markov, we need to have some Markov relationship over the topics. So if you remember here in the generative process, it's not enough that I take this prior, but if I have topic transition matrix, I take this prior as a vector and have a predictive prior as well by multiplying this prior by transition matrix like hidden Markov model. And now I generate a new interest for the user that you haven't seen before. Okay? So if I want to have a predictive model, I take this as a vector, and if I have topic transition matrix and do.
So do you do that intentionally?
We have worked with models that does that, but I'm not covering today. But if you do that, then you will show the user content from these new topics. Like if you want to recommend, for example, an article for the user, you don't only use this smoothed version, but use a predictive version. Like if the user was looking at furniture and housing, and I know from other user who look for housing, look for furniture, now I can show furniture ads to the user. So that's called predictive models, which introduce new topics to the user. Okay, so as I said, for synchronous algorithm, it's useful when I want to sample a global variable or I want to optimize a global variable. So I show you two instances of this operation. One of them when you want to optimize the feature, the matrix which project the user feature into a topic space for a given domain, or when you want to sample a global variable like the global topic trend. And as I said, this requires a barrier, and whenever you have a barrier, meaning that you are as fast as the slowest machine, because everyone has to wait until the slow machine finishes. And as I said, it's very easy to program. It doesn't change the semantic of the graphical model, but it's really slow. So can actually we do better? So one application I will cover here, and then I will try to address this question within the context is graph factorization. So our motivation here is that in addition, for the previous part of the talk, we have items, which were keywords, videos, and so on, and you have the user actually interact with the items. Okay, but we have also data that model how the user interacts with each other. For example, who are friends in G+, or who are friends in Facebook, or when you have Gtalk, which are the users that you talk mostly with. Okay? And we need to combine this information because users who have communication with each other more often, probably they have similar taste. Okay? So we would like actually, and if I have a way of like smoothing the user's interest over the graphs, then I need to combine it with the previous model and have a better model which not only models the user interest based on time or based on prior, just based on his neighborhood of the graph. So I just now focus on this part. Like if I have a graph, how I can factorize this graph. Okay? And I'll make this implicit now. So one example when you can see this graph called natural graphs, is that over the social network graph, mail graph, language graph, and computational advertising between ads and attribute and so on. So graph factorization or matrix factorization in general is the problem here is that you have a graph and you want to assign latent vector with each node in the graph. Okay? Such that based on the latent variable of each user, I can predict what's the interaction with these two users. Okay? So for example, if I have this graph, just forget the first part, if I have a latent variable assigned like low dimensional vector of dimension of in RK for this user and for this user, and I want to predict how many, what is the communication frequency between them, I can model this as a function of this user latent variable and this user latent variable. Okay? So that's just graph factorization or matrix factorization in general. So we observe y, which y is the value over the edges, okay, and want to optimize over these, which is a latent vector for each node, for each vertex. And we want to predict the interaction between I and j as a dot product between these two latent vectors, and I want to minimize the L2 norm between the observed interaction over the edges, the value over the edge, and the predicted interaction. And we just have L2 prior over these so that you don't overfit. Okay? It's just standard matrix factorization. Okay? Which is the same here if you apply it for graph factorization. How many of you have seen this equation before for matrix factorization? Okay, few. Okay, so again, matrix factorization, meaning that I have a matrix Y, which models the interaction between user I and j. And for our purpose, we have this interaction is a real value. For example, if you have a communication graph, the value of Y will be the rate of number of messages exchanged between the two users. And I want to assign for each user I and j latent vector of dimension k. And so that if I do the dot product between zi and zj, I have a prediction yij hat. I want to learn zi and j so that it minimizes the L2 loss between y, the observed value, and the predicted value, and just put L2 regularization to prevent overfittings. That's our optimization problem. So switching gear a bit, we're talking optimization now, no graphical model. Okay. So again, observed value, predicted values, which is like hidden variables, and regularization. Okay. SGD. How many of you know SGD? Stochastic gradient descent. Everyone raise your hand up. Really? Okay. Okay. So SGD is just a very simple algorithm. You have an objective function, and you want to find the minimum value of the variable z. So all what you do is that you know that at optimality, the gradient should vanishes. So stochastic gradient descent is just pick a node zi, compute the gradient of this objective function with respect to zi, and then do a gradient step by changing zi, we want to minimize, so just we do in the gradient descent direction. We just gradient step by multiplying the gradient times some learning rate. Okay? And you continue until the gradient vanishes, until you converge. Okay? And if you get the gradient of the objective function with respect to zi, you get these things, which just you look at all the neighbors of I in the graph. It's just standard gradient computation, just nothing. Okay? That's all what you need to know about SGD. Again, you have an objective function. You pick one random variable, you compute the gradient, and then you do a gradient step over the local variables. Okay? Okay. So the problem is that in order to do that at the scale like mail graph or communication graph or like G+ graph, is the nodes are the user and the edges represent the log number of messages in this application. So here we have like around 200 million vertices and around 10 billion edges. Okay? So if you want to do that in a single machine, it will take forever. So the challenge here is that it's not only take forever, it's also like storage-wise, because if I want to embed the user into like 20-dimensional space, then the state will have 200 million vertices and edge vertices represented as like 100-dimension embedding. That would be huge. That's actually like petabyte of data. You can't fit that in a single machine. So there is no way. So you have to use distributed inference algorithms. And the approach that we use here is that, as we used before, we start to use some of the ideas again that was discussed in the beginning, but we repurpose them as a context of optimization, as I will show you. So we have the graph. We distribute the graph over machines. We need to partition. And then we need to do local update, but we synchronize values using some communication topology. So again, all what I have shown you before is that you partition the problem, you have overlap of the local state, and synchronize it. Okay? We show how you can do that for graphical model. We want to show how we can do that for problem in which you need to optimize some variables. It's the same philosophy, just different incarnation. Okay. So one way of modeling the problem, model it as something called consensus problem. So what does it mean? Let's say we have our graph here. Okay? And we want, as I said, we partition this graph into 3 parts so that each part fit in a single machine. Okay? So each machine will take part of the graph, right? So what's the problem now? We can do like a single machine. I cycle until conversion, each machine in parallel, take a node, look at the neighbors, compute the gradient, and just do a gradient update. Okay? What is the problem here? The problem here is that some neighbors are missing, right? For example, for this part, it's assigned to this machine. When I compute the gradient over this node, it has 4 neighbors here. 3 neighbors are in the same partition, so that's okay. But this neighbor is actually in different partition. He is in this partition, which is assigned here, I think. Okay? So some interaction, some neighbors are missing. Okay? So what we can do from the previous part, we can just replicate. Okay? So once I partition the graph, I assign each partition to a machine, but I also take the closure of this partition and replicate this node in a given machine. Okay? And now we can do our algorithms again. Now, this node, which is this node, so it's replicated here. It has a version here, and it has a version of another machine. So again, this is the local state in this machine, this is the local state in this machine. There must be a global state, and you want to synchronize. Okay? So the same phenomena appear here again. So again, I replicate the closure of each partition, and that will introduce dependency across the clients or across different partitions. So we want to here, instead of like doing this asynchronously, if you apply the star synchronization algorithm here, like you keep delta and send back and forth, that doesn't converge. It actually works very bad. Okay? So we want to have a better method that actually have a tight control so that you don't allow the 2 copies of this node. So this node here has 2 copies, one of this in this partition, and another copy of this partition. You don't want these to diverge from each other because this is a non-convex problem, it's very sensitive to these things. So one way of these problems, this is the original problem, is called a consensus formulation. So this is what it means. It means that I have a local problem, I have a copy of the factor at each machine. This is the local state, sorry, the local view of the global state, which is the copies x, and I have a global factor which we call z. Okay? And now each machine solves an optimization problem over its assigned partition using the local factors. Okay? But I want the local copies of the global factor to be close to each other, so I add a penalty that discourages deviation from the global state. So I want the global state, I want the local copy of xi to be close to the global copy. So I have an L2 penalty over this objective function. Okay? And we call this consensus problem because I have a local problem, which as before, it's the L2 loss plus L2 prior for the regularization, but I add some penalty here that encourages consensus between the local copies. And that's what we have done before as well. So in our previous application, this part was missing, but we enforced that by faster synchronization. So I want to make sure that I send delta back and forth. Here, I want to add this explicitly in the problem and optimize this global objective function. Okay? Okay, so again, the formulation is that I partition the graph, I assign a partition to each node, to each client. You can't now have a local optimization problem over your assigned partition, but you need to borrow some nodes, which is the closure of your partition, and now you are independent. You can work with your local copies, and you still add some part that discourage deviation from the local copies and the global one. Okay, so how we can synchronize? So I have this objective function, and I want to optimize it. So first I describe an synchronous algorithm, and I'll show you the synchronous version of it. Okay, so the synchronous algorithm is very simple. You need to optimize over the local copies and the global copies jointly by using alternating optimization. You fix z. If you fix z, then the local copies are independent from each other, and you now optimize locally this objective function, which you have local objective, which minimizes the L2 loss between y and the predicted value, but you add an L2 regularizer, which penalizes the deviation from your local value from the global value, and the global value is fixed here. Okay? And I do few iterations until you converge to a new local value. Okay? And as you can see, if I remove this part, then the local copies will diverge, but since I added this constraint, the local copies cannot diverge from the global copies. Too much. And then in the second phase, I need to update the z's. So this part does not depend on the z, you just need to minimize. We have a new value of the local copies, and I want to find the z's that minimize the deviation. And as you expect, the solution here is that take the local copies and take their average, and that will be the new global value. And you then iterate. Okay? So graphically, this is how it looks like. So in the global state, we have the values of the replicated node. Okay? And now each machine has its own copies. This is x1, x2, x3. And we only store a replicated node. For example, this node here, this is a bit of optimization, but like for example, you don't have to store this as global because it only appears in one partition. So we only care about the node which overlap in partitions. So this one, and this one, and this one, and these two. Okay? These which are global because they are replicated. Okay? So in the first step, I push down z to each machine. Okay? And each machine has z optimized in parallel. They don't talk to each other now. They optimize this local loss plus the deviation plus these penalties that prevent the deviation from the local copy and the current global value. Once you converge, you just push the local values upstream and then optimize the global values, which end up being just taking the average of the local values. Okay? And then push back the new global values and continue iteration until you converge. Okay? That's synchronous algorithm because in each phase you have to wait until all the machine finishes local optimization, push the new local copies, average them, and push back. Okay? And that converge. And it works well. If you are familiar with something called the keyword here, if you want to read more about that, called ADMM, called Alternated Directional Method of Multiplier, and this is what this technique is about. Okay? And you can apply this to any optimization problem by having local copies and global copies, and you decouple the problem again. It works in practice, but as I said, it has the all disadvantage as any synchronous algorithm is that, again, you are limited by the slowest client. Because you have to wait until the slowest client finishes its local value and send it back. Okay, so and we use the same template as we used before. Barriers, right, all the same thing. So can we do better, actually? So can we do asynchronous optimization with people like just shouts and talking to each other in parallel and random ways? Okay, so the basic idea here, if you see, in the previous algorithm, we do optimization over, we do coordinate descent, actually. We fix z, optimize the local copies, and then we fix the local copies, optimize z. So information takes some time. Okay? So if you remember from the first part, sometimes we say when you collapse a variable, information can propagate faster. So can we do something similar here? So the equivalent here is that instead of optimizing conditionally, you optimize jointly over x and z at the same time. Okay? So you pick a local node, and then you do a gradient step over x and z. But now this is a problem because z is global, so we have to push back and forth. So we need to have smart about synchronization. So how can we do that? So you look at the local objective function. Don't worry too much about the form of the gradient. You can just spend like 30 seconds and drive this. It's trivial. But let's look at the intuition. So given a node like zi, if I pick a node at a given partition, it touches two variables. It touches the local copy at that partition, and it touches the global copy. Okay? I compute the gradient of these problems that you optimize locally with respect to x and with respect to z. Okay? So you have the gradient of the regularization part, and you have the gradient of the loss part. Okay? And you want to apply this to the objective function. You want change z and change x at the same time. Let's graphically see what's happening here. So again, we have same thing as before. You have this partition comes here. We borrowed two nodes because we need them. Okay? And we have this borrowed node. We bought them in the global state. They are in red. But each machine will keep a recent copy of the global state. We call it this orange copy. And I intentionally make it orange because it's not red, because it means that it can be slightly different from the global state. We can allow a bit like of slack here. Okay, and this is just, as we call it, it's a cached value of the global variables. Okay, and now we cycle through the nodes. In a computational thread, we compute the gradient update with respect to this node over x, and we do the gradient step over x. And now the problem here is that when you do the gradient over x, you take the gradient of the loss plus the gradient of the regularization. So the gradient of the regularization depends on the global value, but as I said, we use the cached value. So we have a cache of the global value here, and use it when we compute the gradient over the local copy. But we have a background synchronization thread, as you expect, which brings my cached value up to date. Okay. So now I have been changing x, but I want to push this change to the global value. Okay. So if we see before, we want to compute the gradient. Sorry. So it pushes the local value of x to the global server. So once I get the global value, now I compute the gradient of the condition of this global value, which is just the delta deviation from the local copy to the current global value, and use this as a gradient and do a small step over these. So I want to bring z closer to the local value. Okay? So in the previous synchronous algorithm, I just take the local copies and average them to have the new global one. But now just I have a synchronous thread in the background, which thinks the local copy of the variable, compute the difference between the global and move the global value slightly towards the local one. Okay? So you have a progress towards the global value as well. You don't have to wait until the end. And now we send back the new value and you cache it as well. Okay? So in this case, we are doing actually two threads. One worker thread, change the local value, and one synchronization thread, change the global value and bring the cached copy up to date. And these things work in parallel. Okay? And as you expect, if synchronization is not fast enough, this doesn't work. Okay? But the advantage here is there is no barrier. You don't have to do in two steps where you fix the z, optimize x, and then iterate. You do the same thing jointly. And as you see, the architecture is very similar to what described at the beginning. It's just the semantic of local and global, and the message is different. So you use the same architecture as well to implement this. Okay, so how it works. So this is time, and this is progress. This is the objective function, so lower is better. Using the same number of machines, 200 million nodes, and this was 300, 400 machines. This is the convergence behavior of the asynchronous algorithm, and this is the synchronous algorithm. So as you can see, this linear scale, it's actually order of magnitude better synchronization, okay? Because you don't have to wait for the slope lines at all. And in log scale, and how it works, like it's good, it's fast, but does it actually get you the same value as you get? Because the synchronous algorithm is exact. Does it give you the same value or not? And as you can see, we compare the asynchronous algorithm to a single machine. So we just have a smaller part of the graph. And as you can see, you get actually to the same value as a single machine, which means that you actually don't lose that much of the quality. And as I said, does it scale almost optimal? As you can see, if you increase the number of nodes and linear increase the number of machines, same curve I showed you before, you almost have linear scalability. To get this linear scalability, why we get it here, we didn't get it before, because in the temporal application you have to have a barrier. But here there is no barrier, so that you have almost linear speed up when you increase the number of nodes and increase the number of machines. I don't have time to go over that, but again, just to I glossed over, I didn't tell you how you can partition the graph, but there are many algorithms. And our criteria here, when you partition graphs, there are two criteria. Sometimes you want to minimize the cut, but here we want to minimize the overlap between the borrowed node, because the more nodes which are borrowed, the more synchronization is needed. So if you have a partitioning which you minimize the number of borrowed nodes, that's a criteria. And we have some algorithms to do that as well. I'm not going over that. One cool thing is actually just like, as I told you before, when you work in larger scale system, it's important that you know machine learning. It's important also that you know systems, because some of these things doesn't work unless you really understand how the delays and the failure works. So I give you some example here in this application. So let's say we have a graph and we partition it into 5 partitions. Okay, V1 until V5. And the thickness of the edge gave you the number of overlap between the nodes, the number of borrowed node between the partition, okay? The number of edges between the partition. So as you expect, you need more communication between these two partitions because you have a lot of overlap node, but these two partitions have fewer overlaps, so you need little communication between these two, right? Because here you need to synchronize more variables. So now our idea here is that we said we have, let's say you have a number of machines, and we want to assign, we have 5 machines, and we want to assign partitions to machines. Okay, so what's our criteria? The communication between the machine, it depends whether they are in the same rack or not. This is a network rack. So machines which are in the same rack have very fast bandwidths, communication between them, and machines which are across rack have the bandwidth is smaller. Okay, so in order to assign the partition to machines, I want to make sure that if I assign V1 and V2, I want to assign them to machines which are in the same rack because I need high bandwidths between the two. Okay, so this problem is called quadratic assignment problem, which I want to find a partition, a permutation of the nodes, which permutation is just an assignment, such that if the capacity between C is the bandwidth capacity between machine K and L, and D is the communication requirement between the partitions, we want to minimize this thing. So we want to make sure that machines partition which require higher communication are assigned to machines that have higher bandwidth. So I want to maximize this objective function. This is called quadratic assignment. In this case, the quality of the assignment depends on the relative order pairwise assignment between the node to the machine. Okay. It's in general hard problem to solve, but there are lots of heuristics. So once we get the machine, we do some analysis to see what is the bandwidth between the machines, and then we already have the partition. We solve the quadratic assignment problem, and then we distribute the node, the partition to the machine based on the solution to this problem. Okay, and as you can see, one way to measure the progress is that how fast you can synchronize. This is the time in second, and this is the average communication, average time to synchronize a whole pass over the data. And this is a histogram. How long does it take in second for one client to finish synchronizing its local parameter? This is before solving the quadratic assignment problem, and this is after the quadratic assignment problem. You see, there's a bit more divergence here, a bit more like diversity, more variance in synchronization time. But once you optimize the assignment, you see that you have really you minimize the average synchronization time, and this actually affects the quality of the solution a lot. Because the faster that synchronize, the faster that you can converge. Okay? This is another thing that comes in the interaction between the system aspect and the machine learning aspects. Okay, don't have time to go over the last application, but why are you laughing? It's good. It's a good application actually. But it's again, use the same idea for multitask learning, but you can talk to me afterward if you're interested. So okay, I show you some templates, some primitive about asynchronous, synchronous optimization, and we'll start with graphical model, and we'll see that the main idea is that you partition your data, you have some local and global copy, and have you synchronize these things. And we'll see that just the semantic of the local and the global variables change from an optimization problem to a sampling problem, but it's the same idea, same conceptual idea. And these you can use this as building block in your problem. So some of the variable you can optimize, some of the value you can sample, and now you can see how you can do this thing is you can mix and match. And something actually for future direction or where research is in this area, sometimes you need to have some theoretical bound unguarantees for your algorithms, and there's an active research because asynchronous algorithms are great, but when they fail and when they work. I didn't talk too much about number metric model, but the same technique can apply to number metric base, which you will hear about in 2 days. Another thing is that we assume here that bandwidth is free, right? In reality, when you are in an industrial setting, bandwidth actually is constrained. You have constraints on the bandwidth. So if I'm giving you some constraints, how you can design algorithms which are conscious to that constraints. It's not an easy problem. This is again something in progress. We have, of course, you can do a lot of applications. For example, you can combine graph factorization with LDA. So you can have smooth the document topic distribution over the graph. And one area actually was very interesting is semi-synchronous algorithms. So you want to have some algorithms which actually converge even if synchronization, there is delays, there is constraints. And the basic idea here, you can't actually, it's called semi-asynchronous because you have to have the bounds of divergence between the machines. So you can't go with the fastest machine. You have to make sure that the machines are really not far away from each other. It's called semi-synchronous algorithm. And there is actually a lot of work currently going on this area. Okay, so I'm done. Any questions?
Related to this social network and user interaction with each other. Maybe you have mentioned that, but and maybe I haven't got it right. So could you please comment it again? For example, I have several different types of social interaction networks. Like for example, I have one interaction network with my professor and with my colleagues where I share things in one context, and then I have another network with my family and friends where I discuss things in another context. So how is this handled in the model?
Okay, so I didn't focus about this here. So I show you that if you have one network, how you can factorize it. But if you have multiple network, then one idea you say each user have a factor, global factor, but have a context-dependent factor which is sampled from that global factor. Okay, so you can now say I have main interest, but I change it a little bit when I interact with my family, but I change it a little bit when I interact with my friends. And now you can combine the Bayesian technique I saw from the beginning from hierarchical model with the optimization technique I show here. So that's a good question.
Basically, what we are trying to do now is to learn the behavior of the users and trying to suggest them something based on their behavior. But maybe suggesting them something also change their behavior. So maybe if people are exposed too much to this targeted advertisement, they become a little bit immune to it, or I don't know.
Yes. So actually, that's a good question. So I didn't talk about that today, but there's something called user engagement optimization. And the idea here is that usually it's something called explore-exploit, meaning that all the models that I show here, it's exploit model, meaning that I have some behavior, and I keep exploiting what I learned about the user, so that gives the user the same thing again. Okay? The advantage here is I saw the user clicked on that thing before, so maybe he will be interested again. But the problem is that if it's an ad, for example, there's something we call display fatigue, meaning that if you go to Facebook or Google and you saw the same ad again and again and again and again, you become blind to the ad area because same thing, it doesn't change. Okay? So that's why there's something called explore, where with some probability I introduce something new I haven't seen before. So I don't know what you interact with it, but I just want to explore so that I can see, probe in things that I haven't know about you before. So to balance the explore-exploit ratio, there is a whole area, and it's called bandit algorithm, reinforcement learning. If you hear about reinforcement learning, it's related. It's called bandit algorithms, and it actually try to cover these two things: how I can explore, but I still balance explore and exploit. Does this? Yeah.